Hello, I'm Dr. Nagnath Hulle. In this video, we'll try to solve the problems based on the transient response of RL series circuit. The first problem related to this is, for the circuit shown below, switch is kept open for a long time, switch is closed at t is equal to 0, find the following. We are interested in the calculation of expression for current for t is greater than 0, value of the current at t is equal to 0.25 seconds, value of the current at t is equal to tau, and the time at which the current is 1.2 amperes. And this is the given circuit. This here, this switch was initially open and the circuit was in the stable state, that is in the steady state or in the final state. And in that case, will be the circuit analysis for t less than 0. And similar is the case for t greater than 0. And we will try to find out all these values. Here, the first case or the first part is the circuit for t less than 0. The switch was open, this inductor will be the short circuit. If it is open, in that case the current flowing through the circuit will be 0. Therefore, calculating the current at this instant, that is I of 0 minus is equal to I of 0 plus, which is equal to 0 amperes. That is 0 ampere, or 0 is the initial condition in this case. Now we will draw the circuit for t greater than 0. In that particular case, the switch is closed. This is source driven. Now source is connected to the circuit. That's why it is source driven RL series circuit with 0 initial condition, because here in this particular case the initial condition in this circuit is 0. Now here with this background we will try to find out all these values. Here the first point, the expression for current at t is greater than 0 or for t is greater than 0. Now here the expression for the current for source driven RL circuit with 0 initial condition is given by the expression, that is I of t is equal to Im into 1 minus e raised to power of minus t by tau, or which is very same as a V upon R. In bracket it is 1 minus e raised to power of minus t by tau. First we will find out this value, that is Im and tau, and then we are able to express this value here. Im is equal to V upon R. For this particular circuit, V is 12 and R is 8. That's why 12 divided by 8 is 1.5 amperes is the maximum current in the circuit, which is Im. Similarly, the time constant of RL circuit is given with the expression L upon R. L is 10 divided by its resistance is 8. That's why it is 10 divided by 8. It is 1.25 second is its time constant. Now here if we are putting these values in the standard expression, then here this I of t will become, this I of t is Im and Im is 1.5, means it is 1.5. It is 1 minus e raised to power of minus t by tau, and tau is 1.25. That's why this is the expression for current for t greater than 0. That is nothing but the transient response of RL series circuit. Calculate the value of the current at t is equal to 0.25. But I will take the same expression because already we are aware of the expression, that is I of t is equal to 1.5 into 1 minus e raised to power of minus t by tau. Just we are substituting this value of the t, which is as 0.25. It is 0.25 second, and if we are substituting that value, then this is the mathematical part, and its current at that particular instant is found to be, that is 0.271 amperes. Similarly, is third point in this particular category is value of the current at t is equal to tau. The standard expression is I of t is equal to 1.5. It is in bracket 1 minus e raised to power of minus t by tau, but tau by tau, because t is a tau, and in this particular case its value is e raised to power of minus 1, because tau by tau is it is e raised to power of minus 1, and the current at this particular instant is 0.948 ampere. Finally, we are interested in the calculation of the time at which current is 1.2 amperes. Now I will use the same expression, that is I of t is equal to 1.5 in bracket 1 minus e raised to power of minus t by tau, and here we are interested to calculate the time when the current is 1.2 amperes. Now in this I of t I will substitute it as 1.2, and we will simplify this expression. Now this 1.2 divided by 1.5, the remaining thing is 1 minus e raised to power of minus t divided by 1.25. This division is the 0.8. 0.8 is equal to 1 minus that value. Then I will substitute, shift this value towards the left side and this value to the right hand side. Then e raised to power of that is t by tau, which is equal to 1 minus 0.8, which is equal to 0.2. And if we will take the log on both sides in this particular case, that is the same expression. In this case, if we will take the log on both sides, this anti-log and log will cancel and its value will be t divided by 1.25, which is equal to log of 0.2, and its value of the log of 0.2 is 1.61. This here in this case, this minus t is equal to this value, that is 1.25 into minus 1.61, which is nothing but minus 2.01. And finally, if we are finding its value of the time at this particular instant, which is nothing but t is equal to 2.01 second. Similarly, we have the second problem related to this category is for the circuit shown below, the switch was in the position 1. Switch was in the position 1, that is switch in this position for a long time, that is steady state was reached, and finally switch is shifted to the position number 2, that is here. At t is equal to 0 means at t is equal to 0, the switch is shifted to the position 2. Then we are interested to calculate the following. That is, first is expression for current for t is greater than 0. Value of the current at t is equal to 6.67 millisecond. The value of the current at t is equal to 30 millisecond. The time at which current is 1.75 amperes. And finally, we are interested in the calculation of the expression for voltage across inductor and voltage across resistor. The approach will be the same. First, we will analyze the circuit into the two parts. That is, circuit before switching and circuit after switching. The first part in this particular case is the circuit before switching. That is, t is less than 0. In that particular case, the switch was in the position 1. Means here in this case, this is the circuit. And in this case, if we are finding the value of the current, in this case, the value of the current is not 0. That is, I of 0 minus is equal to I of 0 plus is equal to total voltage divided by total resistance. Total voltage is 100 divided by total resistance is 50. That is 100 divided by 50 is a 2 amperes is the current before switching. The circuit for t is greater than 0. If we are analyzing the circuit for t is greater than 0, in that particular case, the switch is in the position number 2 and the circuit will be something like that. In that particular case, the resistance will be the 30 and its inductor will be the 0.2. These two values will be in the series. In short, the time constant before switching is different than the time constant after switching. Before switching, the total resistance of the circuit is 30 plus 20 is a 50. L upon R is the time constant, because R is a different, that's why before switching and after switching is a different value. But for this particular problem, there is no effect of that change in the resistance. That's why I'm not discussing that particular point in detail. We will try to find out all these values. To begin with, we are interested in the calculation of the expression for current for t greater than 0. If we are looking at this circuit, this is the expression of the current for source-free RL series circuit, because there is no source in the second case, and this expression is I of t is equal to Im into e raised to power of minus t by tau. Here we will find out this I naught, or which is same as the Im. Now this Im is nothing but the current in the previous case, which is 2 amperes. This tau is the time constant for this present case, that is after switching. We are nowhere related to the time constant of the before switching. Now here it is L upon R. L is the 0.2 divided by resistance is the 30. 0.2 divided by 30 will be 6.67 into 10 raised to power of minus 3 second is the time constant. And if we are substituting those values, now here this Im will be the 2 amperes and this e raised to power of minus t by tau, and tau is 6.67 into 10 raised to power of minus 3. Means here this is the expression for current for t greater than 0 for this circuit, which is nothing but the source free RL series circuit. Now here second point, we are interested in the calculation of the current at t is equal to 6.67 milliseconds. Now we will substitute this value of the t, as 6.67 millisecond, and we are able to get that value. Now here in this case 2 into e raised to power of a minus 6.67 into 10 raised to power of minus 3 divided by 6.67 into 10 raised to power of minus 3, which is 2 into e raised to power of minus 1. And if we are finding this value, it will be 0.735 amperes. Here third point is we are interested in the calculation of the current at t is equal to 30 millisecond. We will substitute the value of the t as a 30. Now here in this case, this I of t is equal to 2 into e raised to power of this t, and we are substituting the value of the t as that is 30 into 10 to the power minus 3, remaining everything is the same. And if we are simplifying this expression, we will get its value as 2 into e raised to power of minus 4.49 into 10 to the power minus 3. And if we are finding this value, it is coming as that is 1.99 amperes is the I of t, that is current at t is equal to 30 millisecond. We will try to find out the time at which the current is 1.75 ampere. We will take the original expression, that is I of t is equal to 2 into e raised to power of minus t by tau, and tau is 6.67 into 10 raised to power of minus 3. Just we will put this I of t as 1.75, this is 1.75, this 2 into that is e raised to power of minus t by tau, and we will simplify this expression, that is 1.75 divided by 2 e raised to power of minus t by 6.67 into 10 raised to power of minus 3. If we will simplify, we will get this expression. If we are taking the log on both sides, then this log and antilog will cancel, and its value on the left hand side will be minus t divided by 6.67 into 10 raised to power of minus 3, which is equal to log of 0.875, which is minus 0.133. And if we will simplify this expression, we will get its time at the current is 1.2 amperes is 6.67 into 10 raised to power of minus 3 seconds. Now finally, we are interested in the calculation of voltage across inductor. Here, voltage across inductor, I will prefer to use always in place of using one formula or standard formula, I will better to prefer by using the expression that is VL is equal to L into di by dt. Now here in this case, voltage across inductor is L into di by dt. Already we are aware of this I of t. And if we will simplify this expression, we will get this VL is equal to, our voltage developed across inductor is minus Im into R into e raised to the power of minus t by tau. Here in this case, this is minus Im is the 2 amperes, Im is nothing but I0, which is 2 amperes. R is the resistance, which is 30 into e raised to the power of minus t by tau, and tau is a 6.67 into 10 raised to the power of minus 3. The voltage developed across inductor will be here, it is minus 60 into e raised to the power of minus t divided by 6.67 into 10 raised to the power of minus 3. Similarly, the expression for voltage across resistor, in this particular case, voltage across resistance is given by the formula R into I of t. Here R into I of t is nothing but Im into e raised to the power of minus t by tau. If we will simplify this expression will be R into Im into e raised to the power of minus t by tau. Here I will substitute the value of R, which is 30. This Im is the maximum current before switching, which is 2 amperes, and e raised to the power of minus t by tau, and tau is 6.67 into 10 raised to the power of minus 3. Expression for the voltage across resistance is 60 into e raised to the power of minus t by 6.67. So these are the two problems based on the calculation of the finding the expression for the current, or maybe the expression for a voltage across inductor, or maybe the old expression for the voltage across resistor, maybe the calculation of time, and so on. Now here the remaining cases, that is whenever the source is existing before switching and after switching, that I will cover maybe in the next video. Thank you for watching this video. Thanks a lot.